Hello everybody and welcome back to another video by Funlearn Tutorials. Today's video is a continuation from the episode of learning about the property of reflexivity as a property of the relation. So if you haven't watched that video, I'll be linking it somewhere up here and in the description box below, so you can go check it out because it will be continuing from that particular property. In today's video, we'll be skipping transitivity for the time being and we'll be looking at, so we have already done reflexivity, and today we'll be talking about anti-symmetry and symmetry because of course they sound similar but there's wide differences in between these two properties. So we'll be talking about anti-symmetry and symmetry in today's video. Now the property of anti-symmetry is quite different from the property of symmetry, as I have mentioned before. Let us first start with the property of anti-symmetry. So we'll be looking at the third property, which is the property of anti-symmetry. So the property of anti-symmetry. Now what is essentially the property of anti-symmetry? Let us take any particular, so let us say that the relationship that we'll be talking about is let's say equal to. So we want to talk about this. Or maybe, in fact, we can continue with the example that we had in the previous episode. So we'll be talking about the relationship is greater than equal to. Not just is greater than, but also is greater than equal to. This is the relationship that we'll be using for our illustration and our example. And again, let us say that the capital X set, which is essentially the set from which we take the elements under consideration, as you can see from here. So we'll be looking at the set of natural numbers. So capital X is actually the set of natural numbers or the set of positive integers, as I have explained in the previous video. Now what do I mean by the property of antisymmetry? Suppose you find a particular element small x belonging to the set of capital X. So you take any small x element from this set of capital X or the set of natural numbers, and also you take another element y belonging to the same set, but they are two different elements. That is why I am denoting one as small x and the other element as y. What you realize is you can essentially say that small x is related to y, right? Let's say you can see this. You realize that small x is related to y. That is, x, small x are y holds. That is true. And you realize y is also related to x. So you remember in the previous video I had mentioned that there's a concept of order here. So 3 is not greater than equal to 5, but 5 is greater than equal to 3. So in this case you can see that when I say 3 is greater than 5, the relationship does not hold. But when I say 5 is greater than equal to 3, the relationship does hold. In case of antisymmetry, let us suppose, it's not true for every element of course, but let us suppose that for some two elements of the set, and again, just a disclaimer here, I'm not saying that these two elements are different. I'm just saying for two elements from the set that I have considered, in this case a set of natural numbers, if I realize that small x is related to small y and small y is related to small x, these two need to hold together. So let me just mark that with a red. These two should hold together. If that is true, then for antisymmetry to hold, I will have to be able to conclude, again this is for antisymmetry to hold, I should be able to conclude that x and y are not just related, but they have to be the same element. That is, they are identically equal. They are the same element. Why am I not putting the equal to sign? Because x may be anything. X may be a number, it might not be a number. In that case, I have to say that x is identically equal to y, which means x and y are essentially the same thing. Now let us take an example. What do I mean by that essentially? Suppose I take the element 14. Quite a big number to start with an example. Suppose I take the number 14. So I say x is equal to 14. I say x equal to 14. Now I have to take another number 14. I have to take another number y. Let us say, for example, that I take y equal to 14 as well. Why am I saying y equal to 14 as well? I should be able to choose anything I want, right? But I have to take the assumption that x is related to y and y is related to x. So if I take 14 and if I take any number greater than 14, then only this will hold, right? If I take y is greater than 14, then y will be greater than equal to x, but x will not be greater than equal to y. So just this relationship will hold, but I have to make sure that both the relationships hold. Again, if I take y is less than equal to 14, or if any number less than 14 to be y, then only x related to y will hold, but y related to x will not hold. So I have to take a number such that both these relationships hold. So I have to take a number as such. So basically the twist or the trick is to take two numbers which are the same. We have to take two numbers which are the same. So I have to say that x is equal to 14 and y is equal to 14. Now again, so obviously based on this choice, this particular choice, so note that I have not put here for all x greater than belong to x or for all y belonging to x. If I find two numbers from the set of capital X such that this relationship holds, so I have found two numbers such that this relationship holds, that is 14 is related to 14, whichever way you choose, you can either say x is related to y or y is related to x. Now then, can I conclude that 14 is identically equal to 14 or x is identically equal to y? The answer is yes, of course. Both x and y are 14. So I can say that x is identically equal to y, which means this holds. So the conclusion is that if these two relationships hold, then I can assume or I can say for sure that x is identically equal to y. And in that case, I say that the relationship shows the property of anti-symmetry. So that is the property of anti-symmetry. So essentially this says that given relation is anti-symmetric on n. So it's anti-symmetric on the set of natural numbers. So then what is symmetric? The thing is, the prime difference is, when you talk about anti-symmetry, the focus is on the element, because you conclude, look, these two elements are actually same. So you are actually saying, okay, let's see what is the situation with the element itself, right? You are saying, okay, this is related to this is related to this. Hence, I can say that these two elements are same. So you're talking about the elements. The point of the focus is on the elements. In case of symmetry, so if I talk about the fourth property, which is the property of symmetry, the focus is rather on the relation itself. What do I mean by that? The set of the relationships, the property symmetry can be better explained if I think about R as the set as the relationship equal to. So what do I mean by that? And again, of course, I take x to be n. So we are keeping things simple. What do I mean by symmetry now? If I can say that, let's suppose that I can find one particular, or rather a pair of elements x and y belonging to the set of numbers that I have chosen, and suppose I can say that small x are y. Suppose I can say that small x are y. Then I should be able to conclude. Note that here I had assumed that x are y and y are x, then I had drawn the conclusion. So these two had to hold. From there I had to draw the conclusion. Here the difference is I am holding just one to be true, x are y. I am just saying x is related to y. Then from this statement itself, from this expression itself, I am drawing the conclusion that y then is also related to x. So what do I essentially mean by that? It's confusing, right? What do I mean by that? It's completely different from the set of the relations, the property anti-symmetry that we had considered. Let us say that I take again, I take the number 14, or maybe let's take a different number. Let's say I take the number 9, and of course I can. So now what the focus is, that the trick is that I have to choose another y such that this relationship holds, right? I have to take x and y such that this holds. Remember that in this case the example is actually on the relationship equal to. So I cannot just take anything. I have to take a y such that x equal to y. What does that mean? I have to take y equal to 9. Whatever x I take, I have to take y equal to that value itself. Otherwise, this will not hold. So I have to take y equal to 9 as well. So in that case, this holds. So I can say that x is related to y. So I have chosen my x and y. Now, can I conclude that here I had said that x is related to y because x is also 9, y is also 9. Then can I conclude that y is related to x as well? Can I conclude that y is related to x as well? The answer is yes, because y is also 9, x is also 9. So I can put a relation, I can put an equal to between them. In this case, I say that the symmetric property holds. Essentially, the relationship is symmetric. So the prime point of difference is that in case of anti-symmetry, you take the two-dimensional, the two-directional relationship. You say that x is related to y and y is related to x. Then you conclude that x is equal to y. Here, you say that x is related to x. I don't know about y or x, but I know that x is related to y. And then, based on the relationship, I should be able to conclude that y is related to x. So, these two are the differences between the property of anti-symmetry and symmetry. Though they sound similar, one essentially focuses on the elements itself because x is equal to y. On the other hand, this focuses on the relationship because that is why I have highlighted equal to sign here. So that is the difference between anti-symmetry and symmetry, and essentially this is how you prove whether a relationship is anti-symmetric or not, and symmetric or not. Just a point to be noted: symmetric property does not hold for greater than equal to, and anti-symmetric property essentially you cannot simply deduce for equal to sign. What you can do is you can check for the other ways. So you can do the same exercise using the equality sign, and you can do the same exercise using the greater than equal to or even the less than equal to sign, and see whether the properties hold or not, because it's not true that every relationship under the sun will have to follow all these properties. These are just properties that a particular relationship may or may not hold. So these are essentially the properties of anti-symmetry and symmetry, and in the future